Finally, in this video, we are going to cover some problems using the uh, counting techniques that we already covered in the previous videos. And let's start with this problem, the birthday problem. I think this is one of the most well-known problems in statistics. Suppose that we have k people in a room. Assume each person's birthday is equally likely to be any of the 65 days of the year, exclude February 29, and that people's birthdays are independent. In particular, they are not twins. Okay, what is the probability that two or more people in the group have the same birthday? First, find a general formula and then solve for k. Well, basically, the problem is asking what is the probability of having one or more match in the birthdays. If we use the complement formula, the complement of having more than one match, or at least one match, is going to be the probability of having no matches. And how to calculate this probability? Well, basically, this is going to be the number of people without no matches over the number of possible outcomes. When we are calculating the probability in these finite scenarios, remember the formula that the probability of A is the number of outcomes in A, in this scenario, over the total number of possible outcomes. This is if our sample space is finite. So how to calculate this? Well, the number of possible outcomes is going to be, if we have k people, let's say we have 1, 2, 3, 4, 5. We have k people here. The number of possible outcomes of birthdays is going to be, for the first person, we can pick every day of the year. So it's 365. For the second person, it's going to be the same. And so on. Until k numbers here. And on the numerator, we have the number of people without no matches. So for the first person, we can pick 365 days. But for the second one, it's going to be 364. Because we already picked one of the days of the year. And for the third person, it's going to be 363 days, and so on, until 365 minus k plus 1. And this is going to be 1 minus 365 factorial over 365 minus k factorial over 365 to the power of k. And this is the general formula. For k equal to 30, if we solve, this is going to be 1 minus 365 factorial over 365 minus 30 factorial is over 365 to the power of 30. This is around 0.763. So you have this link to check different variations for the birthday problem. Now consider this last example. a 5-card hand is dealt from a standard well-shuffled 52-card deck. There are 4 suites: diamonds, hearts, spades, and clubs, each with 13 ranks. Numbers from 2 to 10, jack, queen, king, and ace. Okay, what is the probability of select 3 cards of clubs, 1 of spades, and 1 of hearts? Well, we know that we have 13 cards from each suite, right? 13 of them. And we are asked, what is the probability of select 3 cards of clubs, 1 of spades, and 1 of hearts? Well, basically, if we let our event of interest, let's say A, to be select 3 cards of clubs, 1 of spades, and 1 of hearts, the probability of A is going to be, we have in the denominator the total number of outcomes without no conditions. So we have that from 52 cards, we are choosing 5, right? Oh, we are choosing 5. So it's 52, choose 5. We have that combination in the denominator. And for the numerator, we are going to see the number of outcomes of interest. The number of outcomes in which 3 cards of clubs are selected. Well, we have from clubs, we have 13 cards of clubs, right? And we want to pick 3 of them. This is for clubs. From spades, we have 13, and we want to pick just 1 of them. Same for hearts, 13, we're picking just 1. And we can also add, but this is going to be 13. From this case is going to be diamonds. We are not selecting any of them. So it's 13 over 0. 13, choose 0. This is going to be 1. We don't consider this, but it's okay. We can consider it. And this is going to be the probability. We can calculate this, and the result is going to be, is approximately 0.1116. Now for the part B, this is going to be, this was the part A, and for the part B, we have, what is the probability of select at least 3 aces? Well, at least 3 aces, we have, in this case, we have 4 aces. So we select at least 3 aces is the same as the probability of select, let me put it in this way, at least 3 is the probability of select just 3 of them, 3 aces, plus the probability of select 4 aces, right? And what is the probability of selecting 3 aces? Well, from the 52 cards, we select 5 of them. This is going to be the denominator. And the numerator, in what is the number of outcomes in which we have 3 aces? Well, from the 4 aces, we are going to pick just 3 of them. And from the rest of the cards, from the 48, we picked 2 of them. And this is the probability of selecting 3 aces. The probability of select 4 aces is going to be from the, and the denominator is going to be from the 52 cards. We select 5 of them. That is the total number of outcomes. And we want to select 4 aces. So from the 4 aces, we are going to select all of them. We want all the aces being in this selection. And from the 48 cards remaining, we select just 1 of them. And this probability is going to be, for the first one, the probability of select 3 aces, we have that is 0.0017 approximately. plus this probability of select 4 aces is very small. It's going to be 1.84 and 68 times 10 to the minus 5. And if we sum these two, it's going to be approximately 0.001754. And this is the probability of select at least 3 aces in a hand of 5 cards.